Okay, here's the solution to K1. Water flows into a pipe at a rate. So this is the big thing. This R here is a rate, and it's also given away by the units here, cubic feet per hour. T is measured in hours. The pipe is partially blocked, allowing water to drain out at a rate. So they're giving us two rates. R is the rate at which rainwater flows in. D is the rate at which it flows out. Both of these are from 0 to 8 hours, and they give us an initial condition, 30 cubic feet of water in the pipe at time equals 0. So we've got one amount at some beginning time, and we've got two rates, one going in, one going out. How many cubic feet of rainwater flow into the pipe? Here's a classic. They give us information about a rate, and they want to know how much. So we want to accumulate this rate. We do it with an integral, and we integrate from 0 to 8. We integrate R. I would be putting this into effinent and doing it that way. And in fact, this would be perhaps a good problem to plug R into Y1, and then you would effinent the variable, the Y variable Y1. However you do it, there's the answer to part A. It's that integral. If you use effinent, which I'm sure you probably would, you make sure though that you write the integral part. Make sure you write the integrand. Don't just put a bald answer down. Okay, part B, is the amount of water in the pipe increasing or decreasing at the time t equals 3? The amount of rainwater in the pipe increasing or decreasing? Well, the way we can find out whether something's increasing or decreasing is by looking at its rate of change. If it has a positive rate of change, it's increasing. If some function has a negative rate of change, it's decreasing. Do we have the rate of change of the amount of water in the pipe? That's the key thing. The answer is yes. R minus D is the rate of change of the water in the pipe. It's the rate that water flows in minus the rate that water flows out. If you subtract those two things, you get the rate of change of the amount of water in the pipe. That's the key understanding here. You subtract those rates, in minus out, and that gives you the overall rate of change. Now, sorting through all of that, if the overall rate of change is positive, then the amount of water is increasing in the pipe. If the rate of change is negative, then the amount of water is decreasing, and it turns out that the rate here is negative, so the amount of water in the pipe is decreasing at time 3 hours. Easy problem once you realize what the overall rate of change is, this thing. Okay, part C. At what time is the amount of water in the pipe a minimum? Okay, so this is a classic absolute minimum problem. The only problem is it's with kind of a tough function. Here you have to recognize that that is the amount, oh that was strange, that is the amount of water in the pipe at any time t. Okay, this is tough to sort out. Let's talk about the integral first. We just got done talking about this being the overall rate of change. And what do you get when you integrate an overall rate of change? You get the change, the amount of change. That's the amount of change in the amount of change of water in the pipe between time 0 and time t. See, this is a function of t. You give me a time and I'll give you an amount of rainwater. So the variable is in the bound of the integral. What's with these x's? Well, it really doesn't matter what variable you use here, as long as those variables match what's ending in dx. They don't really like using time or t right here because you're using t as a variable there. These x's are also times, but they are times that are moving from 0 to whatever that ending time is. So Sometimes these x's would be called a dummy variable. Most people like to avoid using t, the actual variable, but if you do, it's not a fatal mistake. You won't lose any points. Okay, so the big takeaway here, though, is that integral of a rate is the change in water in the pipe, the change in the amount. Well, how do we find the amount of water when we know the change? Well, there's the starting amount, that 30. So beginning amount plus the amount that it has changed, that gives you the amount at time t. So this is the function we're dealing with. This is the function we need to maximize. So is it maximize or minimize? Minimize, I'm sorry. This is the function we want to minimize. Well, how do we minimize something like this? How do we minimize any function? Well, where can absolute maximums and minimums occur? At critical points and at endpoints. We've got two endpoints, 0 and 8. Now we have to find the critical numbers of this function. What are critical numbers? The place where the derivative is 0 or is undefined. So we have to find the derivative of this function that's underlined here. How in the world are we going to do that? Well, it's easy if you know the fundamental theorem of calculus. The derivative of 30 is 0, and the derivative of this area function, the derivative of this function with a bound here, is that integrand. So the derivative, well, that makes sense. The derivative of the amount is the rate of change of the amount, and we were talking about the rate of change of the amount up here, r minus d. The derivative of this integral is r minus d. It's the integrand with that variable put in. That's the fundamental theorem. So you set r minus d equal to 0, and you find 2 times. How in the world are they finding this? They're graphing r and d, or they're graphing r minus d, these two functions. This is very much a calculator problem here. They are graphing r minus d and finding where it's 0 using left-right guess on the calculator. Then you have to plug each of those two things, or each of those three things, the critical number and the endpoints, into this function. Holy cow, you got to do an integral at 3 different times from 0 to t. Well, you don't have to do that one because the integral from 0 to 0 is 0, so you have 30 plus 0. But you have to do the integral from 0 to 3.27, the critical number that you used your calculator to find. And then you have to take the integral from 0 to 8 of this thing. And that's all, of course, being done on FNN. This is going to take some time. Boy, would you be happy if you stored these like this into Y1 and this into Y2. Sometimes hindsight, though, you never know. Finally, the pipe can hold 50 cubic feet of water before it overflows. For time less than 8, so from 0 to 8, water continues to flow into and out of the pipe at the given rates until it begins to overflow. Write but do not solve an equation involving one or more integrals that gives the time w, so w is a time, when the pipe begins to overflow. It can hold 50 cubic feet of water, and we want to find the time w when the amount equals 50 cubic feet of water. Okay, so what did they do? Well, here's our function for the amount of water in the pipe. That comes from the part before. It looks a little different. See here, t was the variable and x was this dummy variable. Now w is a particular value of t. This, if we knew what w was, would be just a number, but we don't. So w is an unknown here. We have the initial amount plus the change. That gives you the amount in the pipe, and we want to know when is the amount in the pipe equal to 50. We don't have to do anything more than this. We don't have to solve anything. We just wanted, the question asked us to write but do not solve an equation, and we've done that. Okay, that's K1. It's very calculator dependent, and you got to use the fundamental theorem of calculus a couple of different times.